I would like to summarize what all we've learned about electric potential. So first of all, we know a few things about electric potential, like we measure change in potential, okay, and it is given by minus of E vector dot ds vector. Okay. So if you have to find out what is the electric potential between 2 points, suppose we are moving from A to B, so then the potential difference will be VB minus VA minus integral of E vector dot ds vector. So this will be the potential difference between 2 points if there is electric field and you're moving along ds. And the units of potential, it is measured in volts, okay, and it is a scalar quantity. So whenever we are solving any problem, we don't take care of direction, we just find out the magnitude and that's all. Now, in order to solve electric potential between 2 points, you need what is the value of electric field. So in order to find potential, the first step is to find out electric field. So you might have seen that whenever we have to find potential, we first try to see what is the electric field if we are talking about 2 points and we're moving in between 2 points. So electric field is calculated by Gauss's law. Okay, so use E vector dot dA vector will be equal to charge enclosed upon epsilon naught, and find electric field from here, okay, and use this electric field in to find out what is the potential difference. Okay, second thing, now change in potential is also related to change in potential energy. So change in potential energy is equal to Q naught times change in potential. Okay, or you can also say it is minus Q naught integral of E vector dot ds vector, because delta V is this, so it simply replace the value. Okay, and if we are moving from infinity to some point which is at a distance r, okay, then U will be equal to Q naught into V, or V will be equal to U upon Q naught. So it means that 1 volt is, now this is potential energy U, so it will be 1 joule upon 1 coulomb. So 1 volt is 1 joule 1 coulomb. And do not confuse potential with potential energy. Okay, so this is potential energy. So if we have to find out what is the potential at a point due to an extended object, and not a point charge, okay? So if it is a potential due to extended object, then it will be dV equal to Ke dQ upon R. And if it is a point charge, potential due to point charge, will be V is equal to KQ upon R. And if it is an extended object, you just have to take a derivative of it. Okay? So this will be due to extended object, this will be due to a point charge. And from here, for extended object, we will be integral of Ke dQ upon R. Now you need to understand something here, that this charge we using is a source charge. it is not the test charge, the source of electric field, the source of potential. Okay, and this charge is also a source of the electric field and the electric potential. Okay, now let me also just tell you about the peculiar behavior in a conductor. What happens to the potential in a conductor? Okay, potential in a conductor is a constant. So if you have a conductor of any shape, okay, so the potential inside will be constant at every point. So you'll have a same potential at every point. Okay, while outside the potential will decrease with 1 upon r, depending upon what is the geometry of the conductor. Now suppose if you have a conductor and it is attached to another conductor, let us say it has a smaller radius. Okay, so please ignore this. Please ignore this. Okay, so you have a conductor of a larger radius. Let us say it is R1. It is a conductor of a smaller radius. Let us say it is R2. So R1 is greater than R2. Okay, and this wire here, this sphere is the conductor. This wire is a conductor. This sphere is also a conductor. Okay, this wire is also a conductor. Then if this sphere is at a potential V, this will also be at a potential V, and here also will have a potential V. Okay, so if it is V1 and it is V2, so V1 should be equal to V2. This is what it means, that if the conductor is attached to another conductor, then at every point the potential will be same. Now geometry doesn't matter. Okay, so if suppose you have another some other conductor, maybe like this. Okay, so if it is potential V here, it will be V here, it will be V here. If whole of this is a conductor. Okay, so in this one, V1 should be equal to V2. Now it's a sphere, and due to a sphere, the potential is given by, and let's say the charge on this one is Q1 and charge on this one is Q2. So it will be KEQ1 upon R1 equal to KEQ2 upon R2. The potentials will be same. Okay, while you can also find out what is the electric field at this point and electric field at this point. Now electric field is given by KEQ1 upon R1 square, and E2 will be KEQ2 upon R2 square. So E1 upon E2 will be equal to Q1 upon Q2 R2 squared upon R1 squared. And from the equation, from this equation we can say that Q1 upon Q2 will be equal to R1 upon R2. So it will be R1 upon R2 2 square upon R1 square. So it will turn out to be R2 upon R1. So what is the meaning of this? It means that the electric field is inversely proportional to radius. So even R1 should be equal to E2 R2. Okay, so you know that R1 is greater than R2, which means that E1 is less than E2. So if the radius is large, the charge will be sparsely distributed. It will be far away. This is what it means. So the electric field will be lesser. So it means that outside it has less electric field, or I should say a weak electric field. Okay, while here the charges will be very nearby, because you know that the charge depends on radius of curvature. So the electric here will be a stronger field, a stronger electric field. Okay, this is what it means from here, that if the radius is large, field will be small. If the radius is smaller, field will be larger. So if it is E1, it is E2. We can simply say, after seeing this geometry, that E2 should be greater than E1. So this is how we use the potential in a conductor. Okay. Also, I would like to revise with you how it varies with the distance. If it is a spherical conductor, how it varies, but how the potential varies. Suppose now you have a conductor which is a sphere, okay, and it is a conductor. Okay, and so you know how the potential will change. So outside the potential will change with, if this is R, it will be, if the charge on this conductor is Q, it will vary with KEQ upon small r. On the surface, the potential will be KEQ upon capital R, and inside it will be equal to KEQ upon, because it is constant inside. So if I have to plot the potential, electric potential with small r, it has a constant value inside a conductor and it varies outside. So here this potential will be equal to KEQ upon capital R, and here it will be KEQ upon small r. Okay, so it will decrease with r. But you can also plot electric field. How will electric field vary? You know that inside a conductor electric field is 0, so it will be 0, and outside it is KEQ upon r square. Okay, so on the surface it will be KEQ upon capital R square, because small r is equal to capital R, and after that it will decrease, so it will be KEQ upon r square. Okay, so I should have drawn a steeper graph because of this r square dependence. So it means that if it should be more flat and it should be more steeper, maybe like this. Okay, so maybe you can ignore this, because it is varying with r square, so it has to decrease faster than the potential outside. Okay, that's all.